Yes, sir.
Yes, sir.
Yes, sir.
I'm audible, right?
Yes, sir.
Okay, let me start the class. We left at this place in the last class, right? That this is a four-bar linkage mechanism, and these are the four members, two, three, four, and one was the fixed member, which is fixed to the ground. Now they are connected with the help of pin joint or hinge joint. Now, and for the timing, what we have done is we have fixed the member one to the ground. And if I start rotating link 2 as crank, then what will happen that link 4 will also be start rotating. Then again we mentioned that depending on the size of this lens, actually, what will happen that whether it will completely link 4 will completely rotate as a crank, or it will oscillate as a rocker. That depends on the size of these four members, nothing else. Okay. Now, and we tried to find out geometrically if it is possible to find the extreme positions of the link if we know the dimensions. Okay. And we have explained these figures also when it will be double crank, crank rocker, double rocker, and parallelogram linkage mechanism. Then I will extend a little bit, and we have explained this figure also. Okay. Now, suppose this is a four-bar linkage mechanism, same mechanism, and there is a figure here, which is a little bit modification of the uh, this figure. What we have done is that we have removed link three. Okay. Instead of that, we make a circular slot here. Okay, the same radius as that of the link 4, a link 3, so that its center will be here. And within that slot, we place a slider bar. Okay, sliding bar. That means this bar, this link 3 can, the sliding bar can slide along this curve. Okay, the radius of the curve and the bar is framed such that it can easily move in this direction. And
Sir,
yes,
a few people are trying to join.
yeah, that's the problem. Now, so what we have done is this is a four-bar linkage mechanism since somebody has just joined. We remove link 3. Instead of that, what we do is we make a carved circular slot, okay, which is fixed to the ground. And the radius of the slot is such that uh, it will have the same. We have to do something about this. Now, if that circular radius of the slot is made such that this slider block, which is fixed within this slot, can move easily. Okay. Then what we do, we make a pin joint and connected the slider bar 3 with the link 2. Now what will happen? Suppose this is rocking. Okay, it's a crank rocker mechanism. We have chosen the dimension in such a way. Now, as this will rotate, naturally the link 3 will oscillate. Now, in this same case, let him wait. In the same case, what will happen for this one also? Since this is rotating completely, uh, since Otherwise, what would happen? The link 3 would have rocked here. What it will do is the slider block will come sometime here, then it will come here, then again it will come here. That means it will behave as if this link, which is hidden here, uh, is rocking. So, and what we do? So basically, it becomes still a formal linkage mechanism because uh, one member, two member, this is three member, and this is a four member. Okay, fourth member is there, but which is a imaginary member. This member is a imaginary member, but essentially, this mechanism and this mechanism doesn't have any uh, differences so far as the this point is concerned. Okay, then what we do is we slightly increase the radius. If I increase the radius, this will be flatter, but still it will behave in the same fashion. And if I increase this is to the infinity, what will happen? This will become straight. That means this is the position. Now, so what will happen? This is rotating completely. The, the slider is oscillating or reciprocating in a straight line. Now, this is called the slider crank mechanism. But still, we remember one thing that slider crank mechanism is also a four-bar linkage mechanism. It has one bar, two bar, third bar is from here to the infinity, and fourth is the fixed link, which is connected imaginary to this one to that bar. So this is a slider crank mechanism, and this is a very important mechanism. Because main advantage of this mechanism is that see one is having a rotating motion and three is having a reciprocating motion. So we are converting a rotating motion into a reciprocating motion. Uh, the reverse is very useful if we see the engine of a car. Okay, this is an IC engine. Uh, see, yeah, what? I couldn't get you.
স্যার বলছে ওটা কি ডেট সেন্টার?
কোনটা ডেট সেন্টারের কথা বলছে? Yeah, this is the dead center. Yeah, This is almost dead. It's not a dead center. It will still proceed further because if it will be the dead center, then these two lines will be straight line. Actually, it is moving in this direction. Maybe after coming from the dead center, it will. Anyway, now this is the slider cam mechanism. This is the engine cylinder of a car. This is the space where actually the fuel, either diesel or petrol, uh, fuel they enter through some valves. I can show you. This is a actual car engine. Okay, so there is some inlet valve. There is will be some exhaust valve. This is the slider and mechanism. This is the piston. This is the cylinder. Okay, so fuel will be burned in this region, and this will produce enormous energy. By this energy, what will happen? The piston will try to reciprocate in this direction, and as it will reciprocate, this reciprocating motion is being converted to a rotary motion with the help of a slider crank mechanism. Okay, now and for an engine, car engine, actually you will find that this is called the crankshaft. Okay, we have a generally for any car we have at least three-cylinder, four-cylinder engines, and the positions of the crankshaft made in such a way that the firing will take place at different positions, so that it will be more or less uniform. But still, there is a fluctuation of load. In order to remove that fluctuation, we use a flywheel. Okay, this is the flywheel. This is the essential parts of any automobile engine. But our concern is that this slider can mechanism. Now, as it will move in this direction, it will come to one extreme end, and when it will this point will come in this direction, it will be another extreme end. So these internal length we call it the stroke length of a slider. Okay. So, but remember one thing, that slider crank mechanism is a 4 bar linkage mechanism. Uh, this is a 1 bar, second bar, third bar is extended to the infinity, and this is the fixed member with the fourth bar, which will be something like this. Okay. Now, and this is actual engine. Generally, we use for, if it is a four cylinder, we have four cylinder will be there placed vertically. Inlet and exhaust valve are there. Inlet is for the injection of the fuel. Exhaust is for the, after the burning of the fuel, the entire gas will be come out of this. It will come ultimately to the exhaust, and the intake positions, compression, expansion, and exhaust. This will be dealt in your, I think, thermodynamics and I think engine classes, okay, in detail. Now, there's another aspect is the transmission angle. For a kinematic angle is a kinematic quality which gives us a idea how well the force is being transmitted. Because you see that uh, this is a driving crank. So this is a driven crank. Now, force will be transmitted perpendicular this one. Okay, because along the length we cannot transmit any force. So this angle cos mu is known as the transmission angle, and it should have some value. I mean, if it is, this mu is 90 degree, then it will uh, transmit maximum power. But if it is, say, uh, this angle, then there will be a problem with the transmission, because inter force will be along this AB direction, and now no force will be there in order to, sorry, if it is along this direction, okay, then inter force will be along this direction and no force will be there to rotate the link. So this is the definition of the transmission angle. Uh, Two extreme positions of the transmission angle are shown here. You go through it, you will know. And these are shown in terms of the link length. Okay. Now, once we have, so next, now where we were actually, we mentioned that we can geometrically find out the whether a four-ball linkage mechanism is a double crank or crank rocker or anything else. Okay, now, but sometimes it's difficult to do all the geometrical calculation. Now there are some criteria on which actually we can say beforehand from the link lane that uh, whether it, how it will behave. So and another thing is that that is also important, that in this particular four-ball linkage mechanism, we have fixed this member. Okay. Now, if I fixed other members, then the behavior of this four-bar linkage mechanism might change completely. Though four-bar linkage mechanism is a very simple mechanism, but it has so many qualities, varied qualities rather. So now fixing different members once at a time and generating different mechanism, we call it a kinematic inversion. So my next note will be on the kinematic inversion. Kinematic inversions and Grasshopp's criteria. It is observed that by fixing the links of a closed chain at a time, closed chain means four-ball linkage mechanism we are talking about, we can get as many different mechanisms as the number of links in the chain. This process is known as kinematic inversion. A particular four-bar mechanism would behave like a double crank, double rocker, or crank rocker depending on the some relationship involving its link length and type of kinematic inversion. Grasshopp's criteria provide this information way back in, I think, 19th century. It states that the sum of the shortest and the longest link of a planar four. Okay, remember this is based on the planar four-bar link mechanism. See, 17 minutes past, still people are coming. Now, it states that the sum of the shortest and the longest links of a planar four-bar linkage cannot be greater than the sum of the remaining two links if there is to be continuous relative rotation between two links. Sometimes, whenever we give any statement, it will become very difficult to understand what it actually means. In other words, Grasshopp's law states that one of the links, in particular the shortest link, will rotate continuously relative to the other three links if and only if L plus S is less than equal to P plus Q. Alright. What it says that cannot be greater than sum of the remaining two links, longest and shortest link. So this is the longest link, this is the shortest link. And other two links are maybe P and Q. So if it is L plus S is less than equal to P plus Q, then what will happen? That there will be a continuous motion. That means one of the link will have a crank, basically. That means it will have, then if one of the link is a crank, then what will happen? It will have continuous motion related to the other two links. Now, so L plus S is, this is the condition Grasshoppers have given. The proof of this actually given in Ashok Mallik's, Ghosh Mallik's book. You can go through it. I am not going to go for the detailed proof. Now, since it's a four-bar linkage mechanism, I can fix four bar at one at a time, and I can generate four different mechanisms. So the following relationship will hold. There will be four cases. One is if L plus S is less than equal to P plus Q, linkage is known as Grashopp linkage. Four possibilities exist due to the kinematic inversion, naturally. Okay, so we'll condition first, take the condition when L plus S is less than equal to P plus Q. So two crank rocker mechanism are possible. In each case, the shortest link will be the crank, the frame being the either the adjacent link. That means, see, S and L is the shortest and longest link. Now, what is says that two crank rocker mechanism possible. The shortest link will be the crank. This will be the crank, and the frame being either adjacent link. That means in this case, P is the frame, is a fixed one. Okay, so this will result in a crank rocker mechanism. Instead of P, I can make Q as the frame. Okay, this is the case. This will also result a crank rocker mechanism. So S will be the crank, this will be the rocker. Both the cases. Now, any question? One one double crank results when the shortest link is the frame. If I make this as the frame, then what will happen? I'll get a double crank. That means both P and Q will have complete rotation. And this is the condition C. D is one double rocker results when the link opposite to the shortest link is the frame and when S is the coupler. Now, there could be another possibility is that I have fixed this one and this is the coupler. Okay. So this will be the double rocker. If it is a double rocker, as per the Grashopp's criteria, it seems to violate the condition that if they are double rocker, then at one point this will be stopped. Another point when it will come in the extreme position, this will there will be a stoppage, stationary point. So continuous motion is not possible then, but it will be. Because what will happen, you can try it in by your the drawing, that as it will come to the extreme positions, it will come back to the other end. What will happen? This small link will rotate completely. Okay, so it will have a continuous motion. This small the connecting rod or the coupler will have a continuous motion, but still this will lock. This will be behave as a locker. This will behave as a locker, but this will completely rotate. So we have a continuous motion. So this is one condition. L plus S is less than equal to P plus Q. Second is when L plus S is greater than equal to P plus Q. Then all four inversion results double rocker mechanism, because it's violating the Brasov's criteria. As per the criteria, if it is less than equal to, then only it will be continuous motion. So naturally, it will be double rocker. And when L plus S is equal to P plus Q, then four possible mechanisms are those of item 1. So again, it will be four possible conditions could be possible when P plus L plus S equal to P plus Q. The only difference being there will be instances here when links become collinear. That means there could be a condition when they will be in the same straight line. Okay, then what will happen? It will behave as per the Grashopp's criteria depending on whether I'm allowing it to move uh, a- as required. For example, suppose it will be a double rocker in one case. Now I put a prop here so that after coming here, it cannot move in this direction. Then what will happen? This will rotate completely, but it will come back, it will behave as a rocker. But that is if I give some constraint there. Otherwise, it will behave as the condition of one. Okay. Now, the parallelogram linkage in which the equal links are adjacent. This results a parallelogram linkage. All four inversion of this linkage yield double crank mechanism. If the linkage is properly controlled at the uncertainty condition or change point condition, that means in these conditions, collinear conditions. And deltoid linkage in which the equal links are adjacent. Now here you see that uh, they are not adjacent, but if I put 2S and 2L like this, it will result in a deltoid linkage mechanism. Now when one of the longer link is fixed, if I fix down one of the longer link, it will result in a crank rocker mechanism is obtained. When any one of the shorter link is fixed, a double crank mechanism is obtained. If I fix this one, it will result in a double crank mechanism. In this case, one revolution of the longer link causes two revolution of the shorter link. This is known as Galois mechanism. Okay. So this is all about the Grasshopp's criteria basically. How so? Suppose the four links are given, link lengths are given to you, and it is mentioned that one of them is fixed. Then you can now, considering the Grashopp criteria, you can easily tell that whether it will behave like a double crank rocker, or double rocker. Okay, you have to only remember these conditions. That much. Now, and this is happening due to the kinematic inversion. Now, kinematic inversion is a slider crank mechanism. This is a basically a slider crank mechanism. If I fix this one, this point and this outside hole, this one, then basically we are getting a slider crank mechanism. Okay. If I fix this one, number two, then what will get? We'll get a quick return mechanism. That has been used in a shaper machine. We'll talk about the quick return mechanism later on. And if I fix number three, we'll get a oscillating cylinder engine mechanism. Okay, this generally used in a radial engines. We use this kind of mechanism. So you find that we can get three different kinematic inversion by fixing three different linkage of a slider crank mechanism. Okay. Any question? So we have covered till kinematic inversion. Next, I will start analysis part a little bit. What I if I consider, say it again. স্পেশাল বলতে কি মিন করছো? What? Oh, see, we are talking about right now. We are talking about four-wall linkage mechanism with hinge joint only. Okay, very simple mechanism, but with the simplicity also, some complication will arise. For example, a quick return mechanism. Okay, see here, this slider is moving as this is happening, right? So it will give a complication, and it's a very effective mechanism we can result. But let us first try with the four-wall linkage mechanism, its velocity and acceleration analysis. Then we'll come slowly to the complicated mechanism. Okay. Redundancy means no. For four-wall linkage mechanism, we cannot have any structure as such. There will be a motion always. But if it is a three-bar mechanism, then it will be a structure. Who's coming? Who has joined last? Just now, who has joined?
So I have.
Uh, okay. What happened to you? What is the time now? 11:30.
Yeah, so actually I'm not so well.
Huh?
Actually, I'm not so well, sir. So I was unable to join at 11.
Okay.
Sir, I also joined right now. Sir, I joined at 11 o'clock and I left at 11:28 and I just joined now.
Okay. So we'll start with the velocity analysis. Okay. And there is some problems and other things. Now, these okay. These pages, whatever I'll be sending you. This is chapter 3 of Doughty and James. Some of the pages I have just copied, and I'll be sending this handout to you. Okay, but uh, I'll be highlighting the major points. Whatever is written here. Okay. The, okay. Now, since we are going to do the velocity and acceleration analysis, and treatment will be done graphically only for the time being. Okay, we'll go for the analytical case also. Now, uh, a vector, we know vector and velocity can be represented by a vector. It will have a magnitude, direction, and sense. Okay, so some descriptions regarding the vector has been given. See, there is a vector A1, which has been, if I add vector E1A then I'll get the resultant vector AA. Okay. Similarly, the sum of any number of vectors is the closing side of a polygon of which the component vectors form the sides. For example, this is the case. A1 plus A1 A2 plus A1 A3 plus A3 F A will be equal to A. You all know these things quite well, okay? Still it is there. And there is one composition and resolution method. For example, this is a vector. Okay. Now, uh, I can have a component along this direction, A3. Corresponding complementary component, I can have A4, so that if I uh, get the resultant of this, I will get this vector. Okay, that we know. And we can decompose the vector in any way. For example, the same vector I can have a one component along this direction. The corresponding complementary component could be along these directions. Okay, so that the resultant of these two will be this vector. Okay. And in order to represent the vector, see, this is a very old book. Everything has been given in foot, second, then feet, those kind of thing. Uh, but it's a very good book. For representing the vector, we need a space. Representing the vector, we need a velocity scale. Okay, and at the same time, since these velocities will be applicable on the some linkage mechanism, that in order to represent the linkage mechanism, we need a space scale. That means the dimensions of, in order to represent the dimensions of the link on a page, we require a space scale. For example, suppose the link length is 10 meter. Now we can represent that 10-meter link by a 10 centimeter length on my drawing sheet. Okay. Similarly, representing the velocity scale, we have to take another scale. For example, if the velocity is say 100 meter per second, we can represent it by say 10 centimeter length. Okay, and after performing the, okay, let us go on, then we will understand. Now, rotating and oscillating crank. Suppose this is the membrane. Okay, this is the membrane which is fixed to the ground. We are talking about planetary motion only at point Q, and it is rotating with a RPM in or angular velocity omega. Okay. Now, so what will be the, and A and B 2 point we have taken here. What will be the velocity of the point A? Since we know the angular velocity of this object M, and A is a point lying on this object, what will be the velocity of the point A? VA will be equal to omega into QA. And what will be its direction? The direction will be perpendicular to the line QA. This is the velocity in magnitude and direction of the point A, right? No confusion?
No, sir.
Okay. And see, this is the vector by which I am representing the velocity. Okay. What will be the velocity of the point B?
An into QB, sir.
Yeah, omega into QB. Okay. And if I draw with the scale, VB will be the velocity. We give the direction and sense and everything of the velocity at the point B. Instead of again calculating omega into QB, we could have done this one also. Since we know the velocity of the point A is this point, we join A to Q, okay, and draw a line parallel to VA. And if I say this is the velocity of the point B, do you have any objection? without going for
No,
the
sir.
complete. It's okay, right? Because this is a similar triangle. The velocity of the point A and velocity of the point B will be proportional to their distance from the point Q, right? So naturally, QB by QA will be equal to VB by VA. So we are using this similar triangle proposition, and then we find out the velocity of the point B. Now, this is the way we will be proceeding during our graphical calculations. What will be the velocity of the point C? It will be again QC into omega. That will be give the VC. Instead, what we can do is, instead of doing that calculation, we take an arc QC, and then we take it to here, and then we draw a parallel line here. So this length will give the velocity of the point V, C, magnitude. Its direction will be perpendicular to this one. That means if I know velocity at any point of a particular object, then we can find out. And if that we know that object is rotating about some point, then we can find out the velocity at any other points, both direction and magnitude. I repeat this one. See, velocity of the point C we want to find out. What we do is, I take an arc QC, draw this line. From here, I draw a line parallel to this to cut this line at this point. So this is the magnitude of the velocity of C. Because again, this is proportional to their distances, okay, from the center Q. But actual velocity direction will be, and sense will be here. You have to bring it here. Okay. Now, velocity and acceleration analysis can be done in actually four methods. One is resolution composition method, one is instantaneous center method, one is centro method, another one is relative velocity method. Okay. Now, relative velocity method is very good for calculating the velocities and accelerations of other method. I mean, at any other point, if I know the velocity of point on a linkage mechanism. Okay. Now, but we'll start with the resolution and composition method. Okay. Suppose, let us come back to this four-wall linkage mechanism. Okay, this is a four-wall linkage mechanism, right? Now you will find that this link, this is a crank, this is rotating. Okay. And if it rotates, this will also rotate. Now, any point on this crank will have a velocity which will be rotary motion, basically, any point. And since it is rotating, we can find out at any point the directions, magnitude of the linear speed, like if we know n into corresponding distances. This is also true for this one. Okay, because this is also rotating with a constant angular speed. Now, what will happen to this member? What will happen that this member will rotate at the same time there will be a translatory motion. That means the velocity of, for example, velocity at any point on this member will be, linear velocity will be parallel, perpendicular to this line. Similar will happen for this one, but this won't be true for this one because this is at the same time, this connecting rod, at the same time rotating and translating. Okay, so at different point could have different velocity direction. Now with this concept, let us come back to this one. So N is a member, and the velocity of point A is completely known to me. Okay. And the directions of velocity at point B is partially known. That means point B direction is known. Okay. We have to find out the velocity of the point B. How to find out? So what we do is we join AB. Okay. We join the line AB. Now we make a component of VA along the line AB. Okay. What will be this component velocity? If I draw a perpendicular. So A is the yes? Yeah, A cos theta. But we won't do any calculations. We are going for the graphical method. It will be A cos theta if theta is known. Okay, definitely A cos theta. And VA cos theta. Now, what we will do is we drop a perpendicular from here. So naturally, this will be the value of the A cos theta. So we know the component of the velocity of VA along AB. This is the value AA, right? Now, another thing I mentioned in the previous class, also this class, that we are talking about rigid body. What is the advantage of rigid body? And what is a rigid body? That means the distance between 2 points won't change, okay, with time. That is the rigid body. Now, if M is a rigid body, then what will be the velocity of the point, right? Component of the velocity of the point VB along AB will be BB. And this BB will be equal to A. Are you with me? I said that velocity, whatever may be the velocity of B, its component along AB will be this BB, and this BB will be equal to A. It has to be. Provided the member M is a rigid body. Are you with me?
Yes, sir.
Because if it is not, then what will happen? After some time, the distance between A and B will change. As per the condition of the rigid body, that cannot happen. So, velocity component of B along AB will be equal to BB. That is we know. And another condition has been given. The direction of the velocity is known. This is the direction of the velocity, absolute velocity direction. So we can find out, we raise the perpendicular from this one to cut it here. So this will give the velocity of the point B. So that means you find that velocity here is along this direction, its magnitude is A, and velocity of the point B is along this direction, its magnitude is BB1. And it most likely that VA and VB are not equal in magnitude. Direction, so it's completely different. That means what is happening? This member AM is actually rotating at the same time it is sliding. Okay. If it would have only have sliding velocity, then all the points during any line, say, will have the direction and magnitude will be same. It will be parallel if it is only sliding motion was possible, but it is not. Now, let us take another point, C, where uh, A, B, C, 3 points we have considered on the body M. Okay. Now C point, neither velocity nor direction is known. But we know the direction of the velocity of B. We know completely the velocity of VA. Point A velocity we know completely. So how to proceed? Again, we join A and B uh, and extend this one, drop a perpendicular. So this is the component of VA along AB. So naturally, following the rigid body condition, this will be the component of the velocity of the B along this direction, which will be equal to this distance. And if I know the direction of the absolute velocity direction is this direction, then we can find out this velocity. Okay, it is a perpendicular to find out this velocity. So we know the velocity at the point B, velocity at the point A. We have to find out the velocity of the point C. So again, we join AC and BC. Find out the velocity VA along this direction. This will be AA, and cut CC equal to AA. Similarly, velocity of B along BC will be equal to BB, cut CC1 is equal to BB. Okay. Now what we do is, remember this one, we don't do the resultant of these two. What we will do is, we raise perpendicular from this one, perpendicular from this one. This will give the velocity of the point C. Think about it. It's not the resultant of these two. This is the perpendicular raised from here, perpendicular raised from here. Where they meet, that gives the velocity of the point C. Okay. Because these two are not complementary velocities. Because this is a arbitrary direction, velocity of VC along any arbitrary direction we have considered. Similarly, velocity of C along any arbitrary direction we have considered this one. Those should be the component of the velocity along this and along this. So naturally I have to raise perpendicular from here and here to meet it. Okay. These two are not complementary velocities. So that we can draw a parallelogram to get the resultant velocities. Okay. Got it? Then
Yes, sir.
there is another example is being given where you go through it, but the point A and B velocity directions are given, velocity magnitude is given, but AB is on the same straight line, and you have to find out the velocity of the point C. Okay. Now what they have done is basically they assume that this link is rotating about some point. Okay. So this is the perpendicular component. Now if I meet these two perpendicular component along these directions, okay. Now if I join this and extend this to meet this one as if this interlink is rotating about that point. Okay, then only that condition will happen, that this will give the velocity of the point A, give the point B, perpendicular component. So accordingly, if I know this, we can find out the component C. Once we know the component C, we can easily find out the velocity of the point C. It has been explained here in detail. Go through it. Okay. Now, the same relationship is being resolution and composition method has been used to calculate the velocity of a point B when we know the velocity of the point A. Okay. Similarly, they have tried to find out the velocity of the point C also. Like VA is completely known, so naturally we can find out the velocity B, like take a perpendicular direction, we cut this length will be equal to this one. And what will be the velocity direction of the velocity of the B? It will be, since this will also rotate, these are the fixed centers, right? This will rotate about this. So naturally velocity of the point B will be perpendicular to this one. So that direction is known. Once we know the direction, we raise a perpendicular to find out the velocity of the point B. Got it?
Yes, sir.
Now, if we know the velocity of the point B and velocity of the point C, A, we can easily find out the velocity of the point C. just like here, right? That is being explained here. So go through it. Suppose I want to find out the velocity of the point E. How to find out? You join this tip of the velocity to here and draw a line parallel to this one. So that will give the velocity of the point E. Okay. Similarly, if I want to find out a velocity at any point, extended point, we can find out easily. Okay. Same procedure you have to follow. Now, okay, let us do some little bit complicated problem.
Sir, if there are 2 points on a rigid body, A and B,
Hmm.
and we join them by a same straight line, and both have the velocities in the same direction, then all the points lying on that straight line from A to B will have the velocities in the similar direction as A and B.
Well, if it is along AB, then it will have the same thing. But what you say that 2 points on a rigid body,
Yes, sir.
direction of A and B, yeah, it will be same because it is only no 1 minute. It will be same, and at the same time, if it is equal, then it is
No, sir.
translated.
No, sir, they are not equal. Suppose the velocity at A and velocity at B both have the similar directions. Then all the points lying intermediate between A and B will also have the same direction. That's my question, sir.
Uh,
Because in the figure, when you
yeah, it
showed
will
that,
be same direction, same direction. Yeah. For example, this is the case. Suppose this point and this point have same direction. That means it is completely rotating. This is completely rotating about the point Q4. So all the points will have the velocity along these directions. Same
no,
direction.
sir, that wasn't my question. Sir, in the case of a rigid body,
Uh,
sir, can you scroll up a little? Yes, sir, this question.
mhm.
A and B, we know the velocities direction at A and B. Suppose if both are in the same direction, then all the points lying intermediate between A and B will they also have the same direction?
Yeah, they will have the same direction. Because this entire rigid body is rotating about some point, which that point may be outside this member. Okay.
Okay, sir.
That's why, see, in this particular case, they are not parallel. In this example, they are not parallel, actually.
Okay, sir.
Okay. Let us take a little bit complicated member. Okay. Like these are the two, Q2 and Q4 are the two fixed point. It is visible, right? Properly?
Yes, sir.
Okay. Q2 and Q4 are the two fixed point. Now, this is link 2. Okay. From here till going there. This is link 4. Okay. This is link 4. This is link 6. This is link 5. All these 4, 5 and 6 are joined by a pin joint. 2 and 6 are joined by a pin joint. Then 5 and 4 is also a pin joint. Okay. Now, so what will happen that if the link 2 having a extended position at point A, velocity is given. Okay, velocity is given. Now, that means this is rotating about this Q2. If it rotates in this direction, what will happen? This will move in this direction, right? So, about Q2, this is completely rotating. And Q4 and 4 and link 2 are connected with the slider, okay, at the point C, such that the C is sliding along Q2. You got it? You have to understand the problem first. Then only we can go for the solving. That means as Q4 is moving in this direction, this slider will come down slowly along Q2. This is the case. Got it? So what is says that block 3, this is the block 3, slides along link to Q2 dimensions are given. If the velocity vector of A is 2 inch long, that means it is given. Find the velocity vector of B by resolution and composition method. What is velocity vector of B? B is, I think, this point maybe. Okay. We have to find out the velocity. B is this point. We have to find out the velocity vector of B. So how to go about it? Any suggestion?
স্যার ফার্স্টে এফ পয়েন্টের ভেলোসিটিটা বার করতে হবে, মানে
কোন-
ওই রিজিড ধরে এফ পয়েন্টের ভেলোসিটিটা।
এফ হচ্ছে এটা, হ্যাঁ, এফ পয়েন্টটা কিভাবে বার করবো?
স্যার ওই রিজিড
এ
ধরে
পয়েন্টের
মানে
যদি ভেলোসিটি দেওয়া থাকে তাহলে এই পয়েন্টের ভেলোসিটি আমি বের করতে পারবো, রাইট?
হ্যাঁ হ্যাঁ স্যার,
সেখান থেকে আমি এরকম করে এটা বার করলাম, রাইট?
এফ, হ্যাঁ হুম।
আচ্ছা, ঠিক আছে। এবার এই দিকটা
এবার স্যার স্যার সিজির পারপেন্ডিকুলার একটা লাইন টানবো, মানে সিজি লিঙ্কটার।
হ্যাঁ, হ্যাঁ, হ্যাঁ।
তাহলে তাহলে স্যার Q4 এর মানে ওদের ওমেগাটা একই অ্যাকচুয়ালি Q4 পয়েন্টের রেসপেক্টে। তাহলে স্যার মানে অপোজিট দিকে এর পারপেন্ডিকুলার ডিরেকশনেই এর ডিরেকশনটা হবে, মানে জি পয়েন্টের ভেলোসিটিটা স্যার পারপেন্ডিকুলার ডিরেকশনেই হবে এই 4 নম্বর লিঙ্কটার।
হুম।
তাহলে স্যার এরকম ভাবে জি পয়েন্টের ভেলোসিটিটা পাবো।
আচ্ছা, তুমি এই পয়েন্টের ভেলোসিটিটা কি করে বার করছো?
স্যার এ পয়েন্টের ভেলোসিটি তো দেওয়া আছে, আর স্যার ওমেগাও
এই পয়েন্টের ভেলোসিটি দেওয়া আছে।
স্যার ওমেগাও বার করতে পারবো স্যার এখান থেকে। তাহলে স্যার যদি ওমেগাটা বার করতে পারি
তুমি
দুই,
এই
মানে
ওমেগা বার করতে পারছো কি?
স্যার 2 নম্বর লিঙ্কটার ওমেগাটা বার করতে পারছি, তাহলে ওখান থেকে স্যার
হ্যাঁ,
সি পয়েন্টের ভেলোসিটিটা পাবো স্যার,
সি
ওমেগা
পয়েন্টের
ইন্টু
ভেলোসিটি
কিউ টু
পাবো।
সি।
হ্যাঁ, এবারে এবারে এই 4 এর ওমেগাটা কি করে বার করবে?
4 এর ওমেগা স্যার এর অ্যালং একটা মানে স্যার 4 নম্বর লিঙ্কটার পারপেন্ডিকুলার একটা যদি মানে লাইন টানি, ওটা স্যার ওই ভেলোসিটিটা ওই ভেলোসিটিটা থেকে স্যার 4 নম্বর লিঙ্কটার ওমেগাটা বার করতে পারবো। মানে স্যার কি
কি করে কি করে?
ওমেগা স্যার ওই 4 নম্বর যে ভেলোসিটিটা পাচ্ছি, এই যেটা স্যার পারপেন্ডিকুলার সি পয়েন্টের, এই সরি 4 নম্বর লিঙ্কটার পারপেন্ডিকুলার যে ভেলোসিটিটা, ওই
At C
ভেলোসিটিটা
point.
ইজ ইকাল টু অ্যাট সি পয়েন্ট, অ্যাট সি পয়েন্ট
হ্যাঁ, ঠিক আছে।
ইজ ইকাল টু ওমেগা ইন্টু Q4 সি দ্যাট লেন্থ। তাহলে স্যার
ওমেগা তো আমি
ওমেগা
জানি
ইজ
না।
আননোন হেয়ার, ওমেগাটাই স্যার আননোন স্যার। এই পারপেন্ডিকুলার ভেলোসিটিটা তো স্যার বার করতে পারবো এই সি পয়েন্টের ভেলোসিটিটা থেকে।
না, কি করে? তুমি তো এইখানে ডিরেকশনটা জানো শুধু। You
হ্যাঁ
know
স্যার
only
ডিরেকশন,
direction. You don't know the velocity of C point along this perpendicular
বাট
direction.
স্যার সি পয়েন্টের মানে 2 নম্বর লিঙ্কের পারপেন্ডিকুলার ভেলোসিটিটা তো জানি, তাহলে স্যার মাঝের অ্যাঙ্গেলটা বার করে
না,
ওর
না, তুমি
অ্যালং ওই
এইটা জানো, রাইট?
হ্যাঁ স্যার
হ্যাঁ। না, ওটা, তুমি যেটা বলছো এই মাঝের অ্যাঙ্গেলটা ভাগ করে তার
অ্যাঙ্গেলটা,
কম্পোনেন্ট,
হ্যাঁ হ্যাঁ স্যার।
সেটা হবে না। It won't be. That is the problem here. What before solving this problem, I'll try to think, consider you 3 points, okay? P2, P4, and P3. Okay, consider 3 points which are coincident point right now. Okay, একই পয়েন্টে এইখানে তিনটে পয়েন্ট আমি কনসিডার করলাম। ওয়ান ইজ অন লিঙ্ক 2, one is on link 3, and another one is on link 4. Okay. Now, after
Okay.
some time, what will happen? The positions of the point P2 and P4 and P3. See, this slider is sliding. So P2 and P3 position won't be same after some time. But since link 3 is attached to link 4, positions of P4 and P3 will be always same. As this is rotating, positions of P4 and P3 will be same. So naturally, velocity of the P4 and P3 will be always same. But there will be a difference between the velocity of P3 and P2. How to find out the velocity of VP3 and VP2? See, this is the VP2 we know already, because proportionately this perpendicular component we already know. And what will be the directions of uh, this one? This direction is VP3 or VP4, because they are same. Will be that I know, because that will be perpendicular to this line or link 4. There will be another velocity, which is the sliding velocity of this one, which we call it a VP32. That means velocity of the point P3 with respect to point P2. This is the sliding velocity. That is parallel to this one. So what we do is, we draw a line here, perpendicular to link 4. And from here, we draw a line parallel to this one. So this gives VP32. That means sliding velocity of the link 3. This is the absolute velocity of the point link 3. And this is the VP2, point P2. So this is the equation basically. VP3 is equal to VP2 plus VP32. Once we know now, since if I am drawing this one, these directions we know, I will draw a line parallel to this one. So we know this one now. Once we know this one, we can find out directly this one. Okay. Once we know the velocity of this one and velocity of this point, we can find out easily the velocity of this point, whatever called point B. Okay. Got it? You should have some confusion.
Yes, sir. স্যার এইখানেই তার মানে কি সি পয়েন্টে ভেলোসিটি ট্রায়াঙ্গেল একে বার করা হচ্ছে ভেলোসিটি গুলো, যেহেতু ডিরেকশন গুলো জানি আর একটা ভেলোসিটি নোন আমাদের কাছে, তো দুটো পেয়ে যাচ্ছি ওখান থেকে।
অ্যাকচুয়ালি সি পয়েন্টটা ডিফারেন্ট পয়েন্ট, মানে মানে সি পয়েন্টের মধ্যে আমি যদি দু তিনটে পয়েন্ট অ্যাসিউম করি, একটা লিঙ্ক 2 এর উপর, একটা লিঙ্ক 3 এর উপর, আর একটা লিঙ্ক 4 এর উপর, they will have different velocities. Link 3 and link 4 will have same velocities point, but link 2 and link 3 will have different velocities, because there is a sliding velocity attached. Now, you, without assuming these 3 points, you could have done it, but we required this for our acceleration analysis, this concept. Okay, so I wanted to introduce this. You got it?
Yes, sir.
So we can easily solve this one. Okay. What is this problem? Okay, there is some other problem solved here. Oh, same problem, same type of problem. You can solve it. Now, there is another concept. We have so far covered resolution composition method. Okay. Now, there is another concept called instantaneous axis velocity.
Sir, the direction of velocity at c was provided in that case.
1 minute.
The absolute velocity at c, was the direction provided in this case?
Yeah, provided because this is rotating about this point Q4. So direction
Okay.
is provided because C is attached to this link and this link is rotating about this one always. So naturally
Okay, sir.
point you will have a direction perpendicular to this one. It cannot have any other direction.
Okay, sir. From there we calculated VP3 too.
Yeah, yeah.
Okay, sir.
VP32 is the this parallel line, this velocity. This is
Yes, sir.
VP3 actually. This is okay. Now each member of a machine is either rotating about a fixed axis or about a moving axis. This concept gives actually instantaneous axis of velocity. Instantaneously, this moving axis may be thought of as a stationary axis with properties similar to a fixed axis. Suppose the velocity of a point A is given. Both direction and magnitude is given. Velocity of the point B is also given. Direction and magnitude. Now, if these two are given, then can you find out the point about which this entire body is rotating?
Yes, sir. We can draw perpendicular lines
Yes.
from V and VB.
We draw a perpendicular from here, we draw a perpendicular from here, they meet at point Q. This is called the uh, as if the body is rotating about this point Q. Okay. Now it could be either a fixed axis or it could be an instantaneous axis. For example, uh, see the velocity of the point. These two are the fixed axis. Okay, consider out this member AB. The velocity of the point, if this is given, we know that suppose, and velocity of the B is also known. Okay. Now, if I extend that thing, that if I a perpendicular line means this line extension. If I extend this one and if I extend this one, they will meet at some point. So we can tell that as if at this instant the link AB is rotating about that point, right? Because it's following that same concept, that fixed center concept. The velocity of the point A, because these 2 points A and B lies on the link AB. Okay. So what I do is I extend this one, I extend this one. They meet at some point, which could be outside the paper. Okay, some point here, say. So we can say that this link AB is rotating about this point at this instant because, and that's why it is called the instantaneous center for the link AB. Because why instantaneous center? In the next instant, actually, what will happen? This angle will change. So this velocity direction will change. This velocity direction will change. So next instant we will get another instantaneous center, but which is different from the previous one. Got it? So with the present configuration, we can get an instantaneous center of that link, which is called instantaneous center, basically. Now, so suppose this is a four-bar linkage, what I was talking about. This velocity is known, this velocity is known. So we can tell that Q3 is the instantaneous center for this link 3. As if the link is rotating at this instant about the point Q3. Got it? Now, if we know the instantaneous center of a link, then we can find out the angular rotation of the link 3 about the point Q3. How to find out? You extend this one, drop a perpendicular from here, measure this length, and you divide the velocity at this point, divide by this length, you get the angular velocity of the link 3 about this instantaneous center at this instant. Okay. And if it is a perpendicular, then only it will have component along these directions only. Other direction it will be 0. See how they have found out? This velocity is known, this is known. So naturally, this distance will be equal to this distance as per the rigid body concept. And they cut BB1 is equal to CC1 equal to AA1. Okay. And at this point, the velocity of the point B will have only this component because this point is perpendicular to this one. Okay. And naturally, we can find out the angular velocity of the link 3 by B1B divided by Q3B. Okay. Also, it will be equal to VA by Q3A. VA by Q3A. I can measure Q3A, VA we know. So VA by Q3A also we can gives the velocity. Similarly, VC by Q3C will also give the angular velocity of the link 3. Okay. So now instantaneous axis of a rolling bodies. So this is a ground horizontal line. This is a roller which is rolling about this point, about without slipping. Okay. So at this instant, Q is the point at which it touches, and A will give actually the velocity of the roller in the forward direction. That is known already. Okay. Now, how to find out the velocity of the point B? Now, at this instant, the entire body is rotating about the point Q. Okay. So, this is the instantaneous axis of the roller. And what will be the velocity of the point B? It will be, if I join QB and draw a perpendicular, so that will give the direction of the velocity of the point B. And how to find out its magnitude? We know the magnitude of this point E. If we know omega, we can find out this omega, AA. So we draw an arc here, draw a line parallel to this one, and cut off this equal to this one, A. And then we extend this one to cut this direction at this point. So this gives the velocity of the point B. Similarly, we
Sir,
can find out, yes,
sir, here we can join AB and use the rigid body concept to find the velocity of B.
join, yeah, also we can find out that way.
Yes,
Yeah.
sir.
But you need to find out, but this, because you have to consider this case that Q is the instantaneous center, but because we need to know the direction.
Yes, sir. From that we will know the direction
Yeah.
perpendicular to that line.
Yeah, that concept, the instantaneous concept you have to take. Because at this instant, the entire body is rotating about this point. Okay.
Yes,
You
sir.
will find that if it's a cycle tire, okay, if it's rolling completely, at any point, you can find out the velocity direction, which will be joining from here to here. It will be this direction. If consider a point here, you join this one, the velocity direction will be like this. Okay. So with the help of instantaneous center, we can easily draw some problems. Like suppose this is the problem given. Okay. Uh, See, this is the mechanism given. Q3 is the fixed point. This is also this is a slider which is moving along these directions. Okay, which is attached to link 3. Link 2 and link 3 are attached with a pin joint. Then link 3 is attached to link 4 at point C with a pin joint. And link 4 is attached to again another slider at this point D. Okay. The velocity VA is given. That means we know the angular velocity of this link too. Okay. And all link lengths are given. For all this problem, link lengths are given. So if you know the link length, we can find out VA, which is omega into Q2A. This is known. Okay. Now we have to find out the velocity of the point B. Now how to find out this velocity? Now remember one thing. This link 3 is a single link, which is extend from A to C. Okay. And this is the point, slider is sliding along these directions as this is moving. As the positions of A is shifting, the slider is moving along this line. You have to find. We can do this problem with the help of resolution computation method, no problem. But what we have to do is we want to do it by the instantaneous center method. Now, velocity direction, in order to find out the instantaneous center of the link AC or link 3, we need to know the velocity direction at any 2 points. Then we can find out the instantaneous center. One point we know already, right? VA. So I extend this one. Another velocity of the point B will be, since it is always reciprocating in this direction, its absolute velocity direction will be along this line. Always. Okay. So the direction of the velocity of B is also known. So we raise a perpendicular from here. They meet at Q3. Now Q3 will be the instantaneous center of the link 3. Once we know the instantaneous center of the link 3, it's easy to find out the velocity of the velocity. We draw similar triangles because VA know, so we can easily find out the velocity VC. But remember, this Q3 is not the instantaneous center for this link 4. Because it will have a different instantaneous center. Velocity of the point D will be again this direction, always, absolute velocity direction. So what will be and velocity for this link 4, we know the velocity direction VC. This is this one. And this is the direction of the velocity of D. So we can find out Q4. You extend this one perpendicular to another perpendicular. So Q4 is the instantaneous center for the link 4. Once we know this one and VC is known, we can easily find out VD of the similar triangle. Okay. There are some conditions. Okay, there is another problem has been shown here. You will go through it, you will understand the problem. There are two things to remember for the instantaneous center. One is that at any instant, a particular member will have only one instantaneous center. It cannot have two instantaneous center. Okay. And instantaneous center for this link is changing all instant. Whatever instantaneous center is that for that configuration only at that instant. And it will be changing always. Okay. So these two concepts you should remember. So we have covered resolution composition method, instantaneous center method. Centros we won't cover. In next class, I think I will tell about relative velocity method. If I cover that thing today also, it will be too much, I guess.
Sir, will the questions in the exam be process specific, like do using this method or solve using this method?
No, 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 no. You
Okay,
can
sir.
choose any method. Okay. Relative velocity method, I don't want to. Okay. In the next class,